Great. Well, thanks. And we are slightly behind schedule, so I will try to make up for it and not stand in the way of the coffee break. In fact, because I know you must be tired, it's the last talk of the first session. There were many interesting talks. I first want to make us a bit relaxed and enjoy this sunny scene here in this dark room. And I want you to imagine that you are a hunter-gatherer 20,000 years ago standing in this forest. And maybe you can feel the light on your face and you can feel the wind breezing through this forest. You have never been at the precise same spot. So what you see is unique, is new to you. So you have never experienced the same scene. And maybe you're with a few friends from your tribe and you hunt or you gather some berries or something, or maybe you try to catch that wild pig that was just there a minute ago. And it's gigabytes of data per second streaming into your visual senses. And you have other senses as well. You hear every single sound that happens around you. And you can feel any change of temperature and wind, or when you stand in the shadow. You can smell around you. So how does a brain, how do the humans do it? How can we process this information effortlessly? We feel very natural when we stand there. So how does a brain process this huge amount of information? Well, I would argue that to do that effectively and to reason in this novel scene, you have to have a good model of the world that is essentially causal to some extent. So you have to reason about the latent independent factors that give rise to the scene. You have to know about trees, the properties of trees. You have to know about social entities, animals, about the different plants that you can see, how you move in the scene, what actions you have available to you. And the dream is really to get closer to how humans do it. The dream is really how we can develop models and methods and algorithms to build such more accurate causal models of the world in order to allow for planning and action in more and more richer environments. And so is this just a result of evolution? Is this just kind of a consequence of being millions of years as mammals being exposed to this kind of environment, and somehow evolution has figured out this magic recipe? Well, it can't be, right? We humans live in very artificial environments. We see objects every day that have never existed on an evolutionary timescale before, and yet human perception and reasoning is very robust to that. So we have no problem dealing with new stimuli, with our artificial work environments that we live in. It's very different from the environment that was just in the forest. So with this high-level motivation, how can we build probabilistic models or unsupervised models just from a lot of data? We humans get very few supervision. We are able to navigate this world robustly. We are able to adapt to new environments. So in essence, what we should try to do is to build models that equivalently can learn from just large amounts of data and very few supervision. And that brings me to the learning of probabilistic models, in particular unsupervised models. And we have done some research here in Microsoft Research Cambridge together with collaborators on this topic. And I will talk about two particular works that we have done. But what does it mean to learn a probabilistic model? So usually in machine learning, more generally, we assume that there is this true distribution. There's one true distribution that we care about in the world. I call it Q here. And how we proceed then is we build a model. We build a family of probability distributions that we call a model. And we try to identify in this family, using data, we try to identify a representative that is hopefully very close to the true distribution. And that task is called estimation or inference. And hopefully we have a good model class that captures some distribution that's close to the true distribution. And we use different procedures, for example, maximum likelihood or other procedures to try to estimate a good model. So what's really exciting is that in the last 3 years, there has been major breakthroughs in the field of deep learning, or actually at the intersection of probabilistic models and deep learning, that gives us new ways to estimate rich, unsupervised models. And there seems to be 3 principles at the moment how we can do this. So one principle that has been used a couple of times successfully now in deep unsupervised learning is our so-called integral probability metrics. So this is a general class of metrics between probability distributions. And the particular instances that have been used successfully are so-called kernel maximum mean discrepancy methods and recently proposed Wasserstein-Gunn methods. These are instances of integral probability metrics. So more classically, we have the framework of proper scoring rules. For example, the log likelihood function is a proper scoring rule. So if you optimize a log likelihood function over a family of models, you have certain guarantees that ensure that as you have more data, you get better estimates. And one particularly successful instance of that is the variational autoencoder framework. So the variational autoencoder framework is a bound on the marginal likelihood of a rich probabilistic models, and it follows from the proper scoring rules. Another instance would be the disco networks. Maybe you will hear later about this a bit more. And there are connections between them. So disco networks with kernel functions are kernel MMD methods as well. So these are not disjoint as I paint them here. There's rich connections between them. And finally, there is a framework of f-divergences, which has recently come to the surface due to generative adversarial networks. So generative adversarial networks are based on f-divergences, and there are more generalizations, such as the f-GAN or Bregman GAN works, and I will talk about this a bit more. So with a large set of collaborators, both my colleagues here in Cambridge, as well as Microsoft PhD scholars at different universities, and interns that came here, we have explored all three of these frameworks. And who knows, maybe some of you will invent kind of a fourth principle, but these seem to be the promising avenues towards deep unsupervised learning at the moment. So one work I want to talk about a bit more in detail is our NIPS paper from last year. This is the f-GAN paper. It's a generalization of generative adversarial networks. So what are generative adversarial networks? So if you have not been living under a rock for some time, you have at least heard of generative adversarial networks. Now, I don't know whether I should agree or caution when Jan LeCun stands on stage and says generative adversarial networks is the best thing that has happened to machine learning in the last 20 years. I don't know if that statement is true, but it's incredibly exciting from a formal way because it's a new way to train unsupervised models. So how does this work? Typically, what you assume when you have a generative adversarial network is that you have a generator network. What is a generator network? It's a neural network, deterministic, that takes in some random numbers, processes it deterministically, and at the end, a sample falls out of the network. So you have just generated efficiently one sample from this model. So if you repeat this procedure, new random numbers, same function applied, you get another sample. So it's an efficiently sampleable network. But you can't evaluate the likelihood function. So this is also known as a likelihood-free model. It's not because it doesn't exist, a likelihood function, but because it's computationally intractable to compute it. However, you can efficiently sample from this. So you have this generator network in the blue box, and you have a training set of samples from this true distribution. And now, what you do is, you try to play a game. That's how it's usually described. You try to play a game wherein the generator tries to output realistic samples, and another neural network, a classifier, a binary classifier, the discriminator network, tries to distinguish, is it a sample from the generator or is it a sample from the training set? So if the generator is doing a really good job, it will be very hard to distinguish whether the sample is from a training set or from this generator network. And so the adversary tries to really discriminate, and the generator tries to fool the adversary. And mathematically, this leads to, in this case, a simple logistic loss and a min-max numerical optimization problem because of that structure. So this is what I just said. And saddle point problems are technically a bit more challenging than minimization problems, and that is well known in the community that GAN models are difficult to train. So against this background, what we contribute in this f-GAN work is that we generalize the GAN objective to arbitrary f-divergences. And we also have other contributions which I won't talk about today on the theory and some insights, and also on simplified algorithms for the GAN training. So let me get to the gist of this work. Let's revisit the definition of the f-divergence. The f-divergence is a very general class of divergences. It's just an integral defined as an expectation over one distribution, the Q distribution, of a likelihood ratio, and the likelihood ratio is mapped through a scalar function f. And this function f has to satisfy two requirements. It has to be convex and therefore continuous, and it has to have a value of 0 at the argument of 1. And you can see that if the density function p and q are equal everywhere, then therefore the divergence is 0. Right? So this is what makes this a proper divergence. So there's a nice result from convex analysis that every convex function has another object defined, which is a Fenchel conjugate. And this object is really maybe more easily understood verbally. Any convex function f can be represented as a supremum of linear functions. So if I give you a convex function f here, then you can equivalently represent that with a supremum of some linear functions here. right? So if you take at a point, if you take the tightest lower bound defined by a linear function, then you can identify this function. And this is really what is expressed here. F of u can be equivalently represented as a supremum over a family of linear functions. And this coefficient of the linear function is given by this f star. Okay, so this is just a known result. I mean, this existed since the 1920s from Werner Fenchel. So let's just apply that. Let's just start with the f-divergence. And if you forget everything else I said in the talk, just remember this slide is probably the most important one. So we just plug in the equivalent definition of f. Nothing has changed. It's still equivalent. We know every function f has an equivalent definition. And now what we want to do is we want to swap the supremum and the integration sign. And the supremum, this orange term, is defined pointwise for a single argument x. So in order to pull it out of the integral sign, we need to lift that from a pointwise definition to a definition of a function. So we create a new function, capital T, that we can evaluate pointwise. And then you can see that this term inside the supremum, there's a difference of two terms. It distributes with the q of x. And the q of x cancels in the first term and is added to the second term. So what remains is these two integrals with this new capital function t of x. And we have achieved a bound now because this function family, calligraphic T, may be not rich enough to contain all possible functions. Right? If it contains all possible functions, this is an equality. If it contains only a limited set of functions, it will be a smaller quantity. And now this is nicely, as a result, this is a difference of two expectations. So this can be approximated using samples in a mini-batch setting, in a training set setting. So now we no longer need access to the distributions. We can actually obtain unbiased estimates to this quantity using just samples. So we use that with samples from Q, samples from P. And now we can contrast the GAN objective with the f-GAN objective. And we can see that the f-GAN objective is more general and recovers the GAN objective as a special case, where the special case is the Jensen-Shannon divergence. And the Jensen-Shannon divergence was already mentioned in the original GAN work. So this is just a more general viewpoint. And so what are the f-divergences? Well, basically all the divergences that we usually care about, Kullback-Leibler in both directions, Jensen-Shannon, alpha divergences, Hellinger divergence, Pearson chi-square, and so on. So I won't present much experiments on this. We have some experiments and also some advice in the paper. But the pictures you have seen on the very first slide, this is probably state-of-the-art 1.5 years ago in generative models. The field has moved so quickly that now you can see much better images. This is a model trained to produce images of classrooms. It was trained on 200,000 classroom images. And now I move through this latent space, move through this random input space on a continuous trajectory, and I visualize a continuous image trajectory on the output space. And you can see that hopefully all images roughly look like classrooms. There's objects such as tables, blackboards, windows, and so on. Okay, and that leaves me roughly 1 minute until coffee break, but I started a bit late, so I will use a few more minutes. Okay, so now we have this f-divergence. That's great, but already I wondered when I first learned about alpha divergences, I thought, okay, great, alpha divergence is more richer. I can do so many things. What are they useful for? And then basically people say, yes, some alpha divergences are mode seeking, some are moment matching, and it's good intuition, but really operationally it doesn't really help very much. However, what's really nice about the f-divergences is that certain divergences, for example, the reverse Kullback-Leibler divergence, is important as a building block in other things that we do in machine learning. For example, if you want to do variational Bayes, you have to use the reverse Kullback-Leibler divergence in order to decompose likelihood and prior terms, and so you can do variational inference. So having access, or having connected the GAN framework with f-divergences made us excited because suddenly we can now approach traditional problems like variational Bayes using the GAN framework. And that's what we did. So this is work with Lars Michela and Andreas Geiger from the Max Planck Institute in Tübingen. And we call it adversarial variational Bayes, which is just applying variational Bayes using the GAN framework. So there's a couple of applications in the paper. It's an ICML submission. It's an archive paper. It's already online. I want to briefly mention one, which is we apply to variational autoencoders. So variational autoencoders is a very successful class of deep probabilistic models, essentially defining a simple distribution, P of x given z, and then marginalizing over a latent distribution, z, and that gives you a rich mixture of these conditional distributions. So for example, P of x given z could be a normal distribution, and if you integrate over this variable z, it gives you an infinite mixture of normal distributions, which is a very rich model. Very successful, very easy to train, very simple to implement. Why is it called autoencoder? Well, there's this different viewpoint where you can define a variational inference objective for maximum likelihood estimation, which involves another neural network, an encoder, and you piece these two neural networks together, an encoder and a decoder, and that defines a very efficiently computable lower bound on the marginal likelihood. And this is of the simple form. You can backprop through it. It's really nice. So I apologize if I go a bit fast. But the key point is there are some known problems in variational autoencoders. And the known problems are mainly you still require this parametric likelihood function. So you have to decide a probabilistic family, and usually you decide a very simple one, like a normal distribution. So that's a problem that GAN solves. GAN doesn't require an explicit likelihood modeling. Well, it still requires modeling, right? But it gives you more degrees of freedom. So here you are still restricted. You have to define this parametric conditional likelihood model. And the other one that we address in this work is that the elbow, the evidence lower bound, may be very loose. This marginal likelihood bound may be very loose. And this limits what the generative model can learn and is based because this inference network, this encoder network, is very limited in its capacity. So you may have seen plots like this in papers on variational autoencoders, and you notice that the images, so on the left is a test sample, and on the next column to it is a reconstruction from this model. They look sort of okay-ish, but they look a bit blurry, right? And this is this typical image model applied from variational autoencoders. And it's because of both these problems, the weak elbow and the poor noise model. So against this background, we essentially propose to use generative adversarial networks as a variational family. And we have a couple of other contributions in the paper, and we demonstrate this against a couple of baseline methods. So these are all very recent works on improving variational autoencoders, basically improving the quality of these inference networks, and we add one line to it. But I hope a very exciting line. At least it's a different color. Okay, and I go really fast now to not stop you from having coffee. What's the high-level idea? What operations do we need from this encoder network when we train a variational autoencoder? We need two operations. One is to sample from it, and then we also need to compute the log likelihood of it for the elbow bound. So this is either used in the KL term or used in the entropy term, depending how you write down the elbow. And we just get rid of the second requirement. So we only need to sample from the variational family. We no longer need to compute the log likelihood. And what this allows us to do is to use any neural network as a variational family. So what we will do in practice, we will just consume some random numbers from some normal distribution and then map that into an arbitrary different distribution. And so because we no longer have to compute the likelihood, this mapping doesn't have to be invertible, so this gives us huge degrees of freedom. Okay, so how do we do this? We essentially break up this evidence lower bound. We break it up by just expanding the KL term. And then we take this term that remains, the log odds of the prior with the encoder network, and we identify this term with an additional discriminator network. This was a discriminator network part that GANs use. We identify that with a new function, t of x, z, which will be parameterized by a neural network. And then we have some reasoning in the paper that makes statement about the variational optimum of this function, and we can replace the learning objective with just a simple one where t star is the optimum of a variational optimization problem. So we have an additional optimization problem which tries to create an optimal function t, and we know what the fixed point should look like, and we have some quantities about that. And then we have to apply one more thing, which is a reparametrization trick from Dirk Kingma and Max Welling, and that gives us a final reparameterized learning objective, which is an expectation independent of any distribution. So the distribution is parameter free. The epsilon is a noise distribution. And that allows us to do unbiased estimation of every parameter in this learning objective. And we can learn this using neural networks. we have a learning objective, which is essentially like a GAN-type algorithm. Now, here's one slide with algorithm, not for you to look at, but it's actually implementable really easily. Just computing 3 gradients and updating them. And more details are in the paper. There are connections to, more precise connections to f-GAN, to adversarial learned inference, to adversarial autoencoders. There's more theory regarding the approximation that we make, and also maybe from a classical probabilistic modeling perspective, most interesting, you can also do just parameter VB. So instead of doing mean field or other kind of simple VB methods, you can use this as a VB family. We also have experiments for that in the paper. So every paper, maybe not at ICML, but at NIPS, needs to have an experiment on MNIST. So we did one experiment on MNIST because the literature in a VAE field has done this. So here's a lot of VAE models doing binarized MNIST, and these are the log likelihood bounds that they provide. And in every way, we are competitive in terms of the likelihood bound. And we did some needed importance sampling validation of these. So it's a kind of recent and exciting way to do variational autoencoders. And there are some images, and they look kind of sharper. We can do latent image space interpolation between 2 faces. And that brings me to the end of the talk, but I want to conclude that you actually don't have to publish your code anymore. We will publish the code in a week or so. You don't have to publish the code anymore. You just publish an archive preprint, and 2 days later, somebody publishes a TensorFlow implementation of your own work. So you want to check out the TensorFlow implementation. There is one already, and we will also update our implementation. So this is a great way to do VAEs and also parameter VB. And it allows you to do likelihood-free variational inference. So thanks for your attention. So there is a coffee break now until 11:30, but I would propose we extend that by 5 minutes to until 11:35. And coffee should be waiting outside.